do appropriate control in switches. So today we will see that, and eventually we will see sign PWM and multiple pulse width modulation. So we will start with basic single pulse width modulation with some distortion, like some cutout from the pulse. So we call that notch. So we will see what is that. So I will draw a basic single phase inverter circuit here. So this is terminal A, B, our switches H11, H22, H12, H2, and this converter, let us suppose our very common RL type of load. So here we need to control the voltage at output side. So first of all, we must ensure that H11 plus H21 should be 1 and H12 plus H22 should be 1, so that both the switches would conduct in complement manner, and we will give some kind of pulses so that we can control our output voltage, which is nothing but the VAB. Okay. So let me draw the pulses. So this pulse we have seen, this kind of pulses we always give for our convenient. It can be shifted. Okay. So let us say this is H11, okay, and H21 would be just, let me write it, H21 is equal to H11 with shifted by 180 degree. This is nothing but our omega t axis. Now we want uh, some voltage whose magnitude should be uh, like less than Vs. Means we want to operate at below rated condition, so that our voltage, we want to get lower amount of voltage at desirable frequency. So to do that, let me give switching H12, and H12 would have pulse in some manner which is shifted from H11 by, you can say this is the phi angle. Okay. So this switch, generally what we have seen in three-phase inverters, that this was usually B phase, and this B phase was shifted by 120 degree to make things balanced or load balanced. But here we have single phase, so we do not have such constraint, and we can generate our desirable pulse in whatever manner as we desire. To do that, I am sub I am subtracting anyway that VAB would be H11 Vs minus H12 Vs. Okay. So whatever pulse we will give here, that would get subtracted from this H11 pulse, and the remaining portion would contribute to our average or RMS voltage. So let me see what would be the magnitude of, Vs, or sorry, VAB. So VAB is H11 minus H12 into Vs. So we will subtract. So this is leftover part from left side, and negative pulse would go on right side. So by this method, we can achieve lower RMS voltage. You can easily see it is definitely lesser than our single phase full bridge inverter. So I think I started with three phase inverter, then I did not discuss single phase inverter. So anyway, it will get covered in this portion.
Okay, sir.
So for that purpose, now the thing is, for any waveform in power electronics, we need to know Fourier series. So I think we can do that because we know switching Fourier series of H11, and we can calculate switching Fourier series for H12, that is just shifted by phi from H11, and we will calculate VAB. So H11 was half because again it is conducting for 180 degree, from minus pi by 2 to pi by 2. So we can write half plus 2 by pi summation n is equal to 1 to infinity 1 by n sine n pi d, and d is half cos n omega t. And similarly, we can write h12 is equal to half plus 2 by pi is 1 by n sine n pi by 2, but it will be shifted with angle phi in right direction, so we can write as omega t minus phi. Now we can easily write VAB, that is nothing but the H11 minus H12 into Vs, and when we will do subtraction, then this half and this half portion will get cancelled, and we would be left with 1 by n sine n pi by 2. Let me write Vs sine n pi by 2 cos n omega t minus cos n omega t minus phi. And doing further calculation, uh, you will get 2 Vs by pi summation n is equal to 1 to infinity 1 by n sine n pi by 2. And if you do cos A minus cos B, so that would be minus 2 sine B minus A by 2. So sine n omega t minus phi by 2 in sine n phi by 2. So now this is Fourier series, and we got a square waveform. However, it was not full square, but it is in a square uh, pattern. So when we have any square waveform, there must be some fundamental component of that would correspond to sine omega t, and that term is coming out here. You can observe if you put n is equal to 1, you will get fundamental pure sinusoidal waveform along with some other harmonics if you put n is equal to 3, 5, or so on. So again, we can see here our magnitude is 2 Vs by pi. If you do for full single phase inverter where no shift of phi, uh, then you will not get this term sine n phi by 2. So this term is coming due to reduction in fundamental component of our output voltage. So the amount of reduction we want, we can control it from phi, or in other words, we can control it from here, this phi. How much we shift, the higher amount we shift, we will get a higher magnitude. And when you shift phi by you know uh, 180 degree, when it would be 180 degree, then you will get pure pure shifted, like in sense of single phase inverter, where if you put phi is equal to 180 degree, this term would be 90, n90, and n90 is 1. So you will get the magnitude of 2 Vs by pi, which would be maximum for the case of single phase inverter. So we are shifting the phase of second, or we are shifting the phase of B such that we can achieve a control on fundamental component of the voltage. Okay. So any doubt till now?
No, sir, clear.
Okay, thanks. So this is how we control our voltages generally. And just to complete this, I will compute fundamental component of output voltage by putting n is equal to 1. So you will get 2 Vs by pi sine n pi by 2 and sine phi by 2, and this minus 2 would get multiplied. Okay, so you would be getting 4 Vs by pi sine phi by 2. So this is your fundamental component of voltage. Now you can easily observe that by varying this phi, your magnitude of fundamental component will vary. So that was thing with this phase shift control of voltage.
Sir, here in this equation, what negative signify?
Yeah, here negative is signifying that we are doing in, generally you will see this pulse on the right side. Okay, what we are doing, if you shift this pulse to left side, you will get positive. So it is just that how you are shifting this, how switching function you are shifting, right? We shifted right side. If you shift it left side, you will get positive. So it is just how you are treating the waveforms. So basically here this negative sign does not signify much. The majority or the important part is this magnitude. Negative can become positive, positive can become negative. So, you are treating signals. So signals can be negative or positive. So,
Okay, sir.
yeah. But in this method, we do not have any control on harmonics much. Like, uh, we can shift phi from 0 to pi only, right? After pi, we have limits. We will violate. If we shift more than pi, it will again align to H11. If we shift H12 by more than pi, it will be aligned with H11 and we will not optimize or we will not get use of that signal. So basically, there is some limitation of this circuit and no much control on harmonic components. Since, see, you can either control your fundamental voltage or you can control harmonics. You cannot control fundamental voltage and harmonics. So you have to compromise on, single entity. So you have to carefully trade off. Like if you want to remove some harmonic from this waveform, what do you need to do? You need to equate this sign in phi by 2. You need to equate it to 0. But again, if you equate it to 0, then you will lose control on this voltage. The voltage, whatever will come, that you have to accept. So that's the thing with this type of control. You got what I'm trying to convey here?
Yes, sir.
Yeah, so you have only single control. So this was all about fundamental voltage control by phase shift. And that is why people shifted to pulse width modulation, where you can, simultaneously control harmonics as well as your fundamental or any other harmonic component. So that's why pulse width modulation came in picture. Otherwise, earlier people were happy with this kind of control, but people did not get satisfied with only one option. We need more options. So people looked for other things and they concluded that pulse width modulation can become a great use. So that we will see. But before that, we will again go to voltage control of three-phase inverter, and then we will do some this kind of approach, like notch-based approach, and then we will see what we can do with that. If we can do things with notches only, because that sine pulse width modulation is very complicated type of control. You have to care all the things from control perspective, carriers, reference signal. But here we are doing just arithmetically. So it is very simple and elegant. The only drawback is it is not giving you much freedom. So that's why first we will see up to what extent we can control with the help of these notches, and then we will move on to sine PWM. So now we will see three-phase inverter control. And yeah, this expression is very useful. This way AB is 2 Vs by pi. What was that? 2 Vs by pi. N is equal to 1 to infinity. 1 by n sine n pi by 2, or minus you can multiply it here. So minus 4 Vs by pi sine n phi by 2 sine n omega t minus phi by 2. So this expression is important because you would not like to derive this expression again and again. So we will take reference from this signal because this signal is very generic. This kind of signal is very generic in nature. So that will come again and again in all. inverters. So for that, I am just marking it here. Even though derivation of this signal is very, easy, just you need to subtract the two terms. But whatever you prefer, you choose on your own. So let me draw, or let me take this snap of three-phase inverter so that. So this is a typical three-phase inverter circuit, okay, so which is connected. Now we need to generate, some desirable kind of pulses or single notch pulses. So let us see how we can generate that. So for that purpose, again, I will draw all the signals. And you try to draw on your own as well at your home so that you get used to this kind of circuits. Otherwise, many people fear of this kind of circuits.
No, sir, I practiced these waveforms and they are quite easy to draw.
Oh, great, great. So let us name it F1 and let us name it F2. And we are treating these two waveforms so that we get this kind of notch signals. So this will be removed from this waveform, and whatever will be removed, that will get added after pi. So 0 and this is pi. So yeah, so let us say the width of this signal is alpha. Okay, and this is again, 180 degrees, so its C would be half minus pi by 2 to pi by 2. So if we subtract F2 from F1, then this portion would be removed from this F1 and it would appear like a single notch here, and that removed portion would come at pi with inverted. So we will see what kind of waveform we will achieve. It will be interesting, I guess. Because if you understand the waveforms, then it would be easy to solve any expressions. So that's the one thing or one beauty of this subject, power electronics. This is pi by 2, 0 for alpha. And whatever is here, this portion, F1 minus F2. So this portion would go up, right? So one notch came here. So it seems like three notch in one half cycle. So we created this kind of pulses within just a single pulse of F1. So whatever will come, that we will know. And to opt how to calculate Fourier series of this kind of waveforms. Let us name it, H1. H1. We are giving this kind of pulses to this switch, H1. So by the help of that switching function, it would be very helpful just to do some arithmetic calculation, and you will be ready with your Fourier series. Okay? So H1 will be F1 minus F2, and F1 we know. F1 is a typical half duty cycle waveform, 2 by pi n is equal to 1 to infinity 1 by n sin n pi by 2 cos n omega t. Now, the issue remains with F2, and we calculated F2 by treating two signals above. Here F2 is similar to this kind of signal with some shift, right? This VAB signal is similar to F2, and it has shifted with phi. So that we will use here, and I will write F2 as, you know, F2 as, 4 by pi Vs into sine n pi by 2 and all the components. So I will write here F2 is 4 by pi n is equal to 1 to infinity 1 by n sine n alpha by 2 sine n pi by 2 sine n omega t minus pi by 2 with minus sign. So this is the Fourier series of F2, and after doing treatment of F1 minus F2, what we will achieve, that we will see here. It will be half plus, you know 2 by pi summation n is equal to 1 to infinity 1 by n sine n pi by 2, we are taking common, and cos n omega t. No, this much is enough to take common, and we will write all the common terms. So this term is similar to this term. Let me highlight it. This term is similar to this term, and 1 minus 4 by pi, some no summation, sorry, 1 minus 2 by pi, I guess 1 minus 2. Okay, pi we have taken already common outside. So 2 sine n alpha by 2 minus 1 raised to power n minus 1 by 2 into cos n omega t. You can just verify the calculation at your end. So
So
this, yeah,
instead of 1, shouldn't it be cos n omega t from F1? Cos n omega t isn't left?
here,
Yes, sir.
here you are saying cos n omega t should not be there, or what?
No, sir. It's in the equation, and you took 2 by pi summation that term outside common. So in H1
Huh,
is equal to 1 is 1. You wrote 1.
H1 is equal to 1. Here, this
1
one,
by,
right? Ha.
yes,
Yeah, but this cos n omega t is also in common.
yes, sine n omega t minus pi by 2. Yes.
Yeah, yeah, this is getting manipulated, minus 1 raised to power n minus 1. So sine pi by 2 plus omega t or sine omega t minus pi by 2 is generally cos omega t. But whatever would be the coefficient of n, that would determine this sign. So to do that thing, we are doing this operation minus 1 raised to power n minus 1 by 2. So if you take n is equal to 1, then it will give us minus cos omega t, right? So that this equation will give you. Any issue still there?
No, so got it.
Yeah. So that is being taken care at this side, and this one is corresponding to F1, right? So this is corresponding to F2, and cos n omega t is becoming common. So we want all the terms in a single frequency coefficient. So that's why we manipulated the equation in terms of either cosine or sine. So it was easier in form the cosine equation. So that was the purpose there. So this equation got solved, then you can easily write H3 in similar manner, just with the shift of 120 degree, whatever we were doing earlier. So again, sine n pi by 2, 1 minus 2 sine n alpha by 2 into minus 1. This minus 1 terms is multiplied with only this term, right? I should, yeah, so this is the thing, and cos n omega t. Okay. Oh, sorry. Cos n omega t minus 120 degree minus 2 pi by 3. Similarly, we can write for h5 plus 2 pi by 3. So that's the thing, and this is the Fourier series of our this kind of pulses if we give. And now finally we will compute VAB, and VAB is nothing but VAB is our H1 minus H3 into Vs, and after doing manipulations you will get to Vs by pi summation n is equal to 1 to infinity 1 by n 1 minus 2 sine n alpha by 2 into minus 1 raised to power n minus 1 by 2 into sine n pi by 2 and cos n omega t minus cos n omega t minus 2 pi by 3. So this is the expression of VAB, and if you wish to compute fundamental component, so you can appropriately put VAB1, and you will get 2 Vs by pi 1 minus 2 sine alpha by 2, okay, and minus 1 raised to power 0, that would lead to 1. So the sign would be still positive, and sine n pi by 2 is 1 again. So the expression would be cos omega t minus cos omega t minus 2 pi by 3. So this is your fundamental component, and after solving it further, you will get 2 Vs by pi 1 minus 2 sine alpha by 2, and cos A minus cos B is again uh, you know uh, 2 cos A plus B by 2. Sorry, cos A minus cos B was, yeah, minus 2 sine, in it will come in sine term. So minus 2 sine A plus B by 2. So that would be omega t minus pi by 3 into sine pi by 3, I guess. Yeah. So sine pi by 3 would come out to be root 3 by 2. So minus 2 root 3 Vs by pi 1 minus 2 sine alpha by 2 into sine omega t minus pi by 3. So this is your whole magnitude of fundamental. Okay. So now you can see here uh, your this waveform contains this alpha. Okay. So based on this alpha, whatever the value of alpha you are giving, that much of voltage magnitude will get reduced from VAB1. So the purpose of this expression was like you can simultaneously control the voltage and at the same time you can reduce the harmonic component. So, but you will be able to control like only one harmonic here since we have only 1 degree of freedom in this expression. So for that purpose, let me show you some harmonic things. Or first, it is better to compute some other phase value or phase to neutral value. So VAG is, as we have seen earlier, Vs by 3 to H1 minus H3 minus H5. Yeah, any issue till this point of expression of VAB1?
No, sir.
Okay, fine. So we can compute VAG as well. So we can control either harmonics from line as well as phase. Or anyway, in some cases, phase and line is just related with the factor of root 3. But again, there is no harm to see what will be the magnitude and expression of VAG. So it would be uh, 2 Vs. I am directly writing the values. You can easily do the manipulation of 2H1 minus H3 minus H5. So just to save some time, I am directly writing it here. 1 by n 1 minus 2 sine n alpha by 2 sine n pi by 2 2 cos n omega t minus cos n omega t minus 2 pi by 3 minus cos n omega t plus 2 pi by 3. Because this, phase voltage contains all the switches H1, H3, and H5. So you will get all the phase values or all the phase switching functions. So that is reflecting here, n omega t correspond to H1, n omega t minus 2 pi by 3 corresponds to H3, and n omega t plus 2 pi by 3 correspond to H5. So this is a typical switching function, and if you further solve it, so what you will get 2Vs by pi. I am just writing the final expression 1 minus 2 sine n alpha by 2 sine n pi by 2 and cos n omega t. Yeah, so this would be your final expression of phase voltage Fourier series, and you can put appropriate value of n to control the voltage magnitude of your phase as well as to control the harmonic component of your phase. So I hope it should be clear. And
Yes, sir.
yeah, and you try to solve at your end also once, so it will be very clear. And further, further, so we saw one pulse or one notches with PWM. Now we can see with two pulses, and then you can generalize it for multiple pulses. So we will see PWM with two notches. Okay, so again I have to draw the waveforms. So this will be minus pi by 2 to pi by 2. Now we are giving two notches, so we need to give two signals, and I would try to remove one notch from here and one notch from you know here. So let me draw the notch signal. So this was F1, let's say this was F2, and whatever we are removing from this portion, I will add at shift of pi. So I am adding it. Let's say this is the angle. Let me define some angles values. So I am calling it beta. I think you can relate with multi-pulse width modulation. So this is similar to that. If this is beta and its width is again alpha, okay. So if it is beta and it is shifted by pi, so it will be this pi minus beta, right? Again, I will give one more pulse so that I make it more distributed, as you might have seen in machines also. Earlier, it was concentrated at one place, so it was producing maximum magnitude of back EMF or induced EMF. if you recall from machine concepts winding factor concept, so when it was concentrated winding, it was producing maximum winding factor of 1. If you remember, Kw1 is used to be 1 for concentrated winding. And as we distribute it for distributed winding, our winding factor depends on how much we are distributing sinusoidally. So its magnitude will always be less than 1. However, its MMF component would be more sinusoidal. Are you able to relate that concept? And
Yes, sir.
yeah, similarly, it is happening here also. We are trying to distribute it more uniformly so that it will not get concentrated at one place, and at the same time, its magnitude is getting reduced, whereas we are removing the harmonic component so that it is getting more sinusoidal. So that is very good analogy I connected. I don't know how. So again, from beta, I will remove this notch, and one more pulse would be from. So this was beta, and this is beta minus pi. So now we are going to draw the resultant waveform of our pulse, which kind of pulse we will achieve at the end after removing so many notches. So first, this component would be there. Sorry, this much component would be there. So I will draw. Okay. Yeah. Now this much would be blank, and again from minus pi by 2 to that point, this function is h1, and it corresponds to f1 minus f2 minus f3. Okay, so further, 0 pi by 2, and this would be minus pi by 2. So these two notches were removed. These two notches were removed, and they are getting added at this portion. That is, I think this is not appropriately placed. So this portion would get added at pi. So the added portion I would like to denote with some other color. So And since this pi minus beta, I should have indicated some further right away, but this waveform is getting a bit. Now again at pi minus pi, there will be two notches that correspond to pi minus beta and pi plus beta. So this is looks like that. Uh, it looks like more distributed, sinusoidally distributed. So if you construct or if you equate Fourier series, you will get some more control on harmonics. So that we will see. So now I will move ahead with Fourier series expressions. So that H1 is F1 minus F2 minus F3. And this is how this H1 would look like. And this kind of pulse we are now giving to H1, first switch of this converter, right? This H1, this H1 will get, huh. So this H1 will get this kind of switching function. Now we will compute our Fourier series. Again, a bit tedious task, but I will try to keep some a step so that you can solve on your own. So H1 is F1 minus F2 minus F3. So F1 is again conventional half plus n is equal to 1 to infinity 2 by pi 1 by n sine n pi by 2 cos n omega t. This was corresponding to H1, F1 and minus F2. So F2 we had calculated in previous case. So that I will write directly. This F2 waveform is similar to the waveform what we derived in output voltage of single phase voltage control with phase shift. So that's why I told there you can make it as a reference Fourier series or reference waveform. Otherwise, you can calculate, but it will consume lot of time. In alpha by 2 sine n pi by 2 minus 1 raised to power n minus 1 by 2 cos n omega t plus beta. Okay, minus 4 by pi n is equal to 1 to infinity 1 by n sine n alpha by 2 sine n pi by 2 minus 1 raised to power n minus 1 by 2 cos n omega t minus beta. So it was shifted, you know, left. So, sorry, right. So it is minus beta and it was shifted left. So plus beta. So now you can solve this equation and that will give us H1 and I am going to write the final expression and that would be a bit longer, but this is what it is. I can't help much with this kind of circuit. However, derivation of this is easier, but calculation is a bit tedious. Sin n pi by 2 cos n omega t is common. If you solve cos n omega t plus beta, cos n omega t minus beta, you will get this final expression And this is very generalized where beta and alpha could be any value. So if you wish to remember this one, two, or three Fourier series, it will be fine. Otherwise, you can derive it at any time. Sine n alpha by 2, sine n pi by 2, cos n beta minus 1 raised to power n minus 1 by 2 cos n omega t. So finally, we achieved in format of cos n omega t. So it has two components here, and you know you can control either from this alpha, this beta, yeah, this beta, and this pi by 2 was already there. So, you know, you can vary alpha and beta. So now you have two degree of freedom, alpha and beta. So it will be helpful in reduction of, your harmonic component as well as control of your magnitude of voltage. So generally in sine PWM, based on carrier and reference, there the number of notches are very high. The number of pulses are generally very high. So the reason of getting more terms in the reference of alpha and beta, so there would be multiple and variable references. So there you can be able to remove multiple harmonics, and at finally uh, people get very sinusoidal like waveform of current and voltages. So that we will again see, I think, I hope in next lecture. So I wanted to conclude it here. We calculated H1 for our two notch PWM. So any doubt in this?
No, sir, clear. And I got to know why we get those too many high notches, although we just learned the concepts, not concept, but that's the reason they are high notches to get more sinusoidal, but now it's more clear.
Oh, great, great. Thanks a lot. So in next lecture, we will continue it from here, and we will see